All right, and so we want to do this chart stuff and so forth. And then there was a max min problem. Oh, okay, I needed the other page. And then the last thing then was this idea we talked about a function being continuous at a point, and continuous means you don't lift your pencil, right? And so continuous and differentiable. Those are two terms that we need to know. All right, for our quiz tomorrow. And so continuous, and we talked about this on Friday. So continuous, the function must be defined, has to have an output, the limit must exist, okay, and those two have to be the same. Like right here, that would be true. The limit would be here, but the output would be here. It's still not continuous. You have to lift your pencil. So, and then we talk about differentiable. Differentiable, these two functions would both be continuous. You don't have to lift your pencil ever, right? They're continuous. The limit always exists. The cars always meet. There's outputs everywhere, right? I mean, that's all good, but the derivative doesn't exist everywhere, right? So that's again, talking about the difference between limit and derivative. A limit cannot exist, right? That's when the cars don't meet. A derivative cannot exist. That's when there's a sharp point or a vertical tangent. So again, we got to keep straight that difference between when the derivative exists versus when the limit exists. They're two different questions. Okay, so a limit does not exist when the cars don't meet. If you get like 6/0 or something, those are times we said limit does not exist. Derivative doesn't exist, sharp point, vertical tangent. And if the derivative doesn't exist, then the function's not differentiable. And then the last thing I would say about that is, kind of like a square and a rectangle, differentiable functions are always continuous. But continuous functions are not always differentiable. And that's these two examples right here. These are continuous functions, but they're not differentiable. Okay, so those are some problems then we can talk about. So let's do some examples of those kind of things. Let's just start right off with this problem right here. So let's say I gave you this problem. F of x equals 2x squared minus x plus 1. Find f prime of 3 by the definition of the derivative. So, Sandy, you weren't here yesterday, so obviously you've figured out here we moved our quiz to tomorrow because of the math and later. And so there's a video what we did. We did some stuff yesterday that was new that is not on the quiz. Okay. It will be so as far as the quiz goes, you haven't really missed anything back. All right, here we go. Let's do that. All right, I'm going to uncover it here. If you want to look. Not ready to look? Right, so the key is the definition of the derivative. So setting that up right there. And then f of 3 plus h means to put a 3 plus h in for that x and put a 3 plus h in for that x. So that's this first part right here. And then put a 3 in. So that's 16. And so right here then you should have 18 minus 3 is 15 plus 1 is 16. So those three. And then subtract 16. So that all 12h take away h is 11h plus 2h squared. Now we can take out an h. And the whole reason for doing that is so we could let h be 0. And so when we can finally at the end put a 0 in for h, we get 11. Now, of course, since we've learned our shortcuts, we do know that one thing I mentioned yesterday, remember, is if you want to find f prime of 3, another way with shortcuts is find f prime of x, right? Find f prime of x. Well, what would f prime of x be in this one? 4x minus 1. So on the quiz, you certainly could do that as a check, right? 4x minus 1. Now, if f prime of x is 4x minus 1, f prime of 3 would be a 3 plugged right in there. 12 minus 1 is 11. That's sure a lot nicer than having to go through all that, right? And that's what we will do as we move on throughout the year. We will hardly ever do this. Now, when we come back and get ready for a midterm, the final, the AP test, we're obviously going to have to revisit this and remember this and so forth, because these things do come up there. But for the most part, we'll get to use those shortcuts. But on the quiz tomorrow, that would just be to check, right? If it says by the definition of the derivative, we're doing it this way here. All right, go ahead and get your calculators out. Go ahead and get your calculators out, and let's do one. So that one would probably be on the no calculator. Now, to be honest, I could put it on the calculator part. It says by the definition, which means you've got to go through all those steps anyway. So remember, just because a question's on the calculator part of the quiz doesn't mean you're going to use your calculator on every part, right? Because there are certain things, it's like the local max-min problem. We'll talk about that later as well. But clearly this one that we're about to do would be on the calculator part. So let's do this. Let's say I had the f of x equals tangent x, and I said find f prime of 2 by the definition of the derivative. Or sometimes it's called the limit definition of the derivative. That is the same thing, the definition of the derivative, limit definition of the derivative. Okay, so there you go. Now, I also would probably say in here, justify your answer with a calculator table. So there would be additional directions here. So this is clearly a calculator one. So we have to set up the definition of the derivative and then go to our calculator as we did on those worksheets using the table. So go ahead and do this one. And again, be sure and show your setup. Even though we're using the calculator, you will be given points for your setup by the fact it says by the definition of derivative. I've got to see what it is you're putting into your calculator. So you have to have that on your paper. All right. So let's take a look here at, so you're on to your, thing is painfully slow right now. Okay, so into our graph screen here, we would, well, let me get it set up for you. Let me show you the setup here, right? So using the definition of the derivative, of course, means this guy right here, right? The definition of derivative, probably not a point, I mean, you don't have to write that, the F notation, I just think it's really good to, because then you say, all right, F of 2 plus h, that means put a 2 plus h in for x, so you get tangent of 2 plus h, and then put a 2 in for x, and you get tangent of 2 all over h, and then it's this red guy here that we're going to put into our calculator, right? Just like that last worksheet we did. Except when you put it into your calculator, what do you got to do? You got to use x's, not the h. Don't put the limit into there. Always see people doing that. When they go to type it in here, they'll type the limit, and that's not what we want at all. So we want a fraction here, and so we want tangent, which is that one, 2 plus, and we have to put a x in there instead of an h, and then we're going to have minus, and then it's going to be tangent again, of 2 this time, and then we're going to go to the bottom and put an x in place of an h, and we're going to hit enter, and then we're going to hit Control T to give our table up there, and then we've got to go to our table setup, which is in menu. Number 2 is table, number 5 is table settings. You should have done this a million times on your worksheets. And then I'm going to do, it turns out on this one, well, we said 3 zeros is probably enough. Is that what we said usually? I think on this one, I'm not sure technically it is. All right. Okay, as I was saying, technically, you know, how big a deal this would be, I think it's a little bit of a big deal, but it's probably not huge. But right here, we're supposed to be accurate in the third decimal place. And so you got 5.775, and here you have 5.773. So a pretty good bet is it's meeting at 5.774. You know, I would say if you get that, that's okay. We really want to see that the cars are meeting at that point, right in there. And so we could put those in there. So I think that's okay. If they're much farther off than that, then I say that's not very good. 7.7, what was it? 5.6 something. And this was 5.773. Or do I have those backwards?
Yeah.
This is right. 3.1. And then 5.77. 1.8, okay, whatever. So put those in there. So I think you can tell. I think your answer would need to be 5.774. Now, it's probably better if the two right near 0 on each side are the same at the third decimal point. So you could just go in and put another 0 in. Put another 0 in your table setup. And then, you know, and get them to agree in the third decimal is probably better. If these were off a ways in the third decimal point, you know, several, and then you're kind of guessing, I think you could be off. It's a kind of a technicality, but we probably should pay attention to that a little bit. Okay, so a problem like this probably worth 3 points or so. Probably a point for setting up your limit here, showing your table, getting the right answer, kind of thing. Okay, so there you go. Now keep in mind, I could just give you some limit problems also, probably will, where I just give you some limit problems and say use your table. You know, limit as x approaches 3 of x minus 3, and then up here would be like 1 over x minus 1 over 3. You know, something like that. And I just say use a calculator table, right? So it doesn't have anything to do with a derivative or anything. Right? It just, so you go into your f of x, you put in this function, you'd set your table to 3. Now this came up in the other class, so let me, in case anybody's wondering about this, notice how our limit here is approaches 0. And in here, this line, we use 0. Did anybody think about having 2 there? Because somebody asked this in the other class. Okay? They said, why wouldn't there be a 2 there? Well, why isn't there a 2 here? Because it's what the limit is approaching. As h or x, in this case, is approaching 0. This is 0. This doesn't have anything to do with it. This 2 goes into the limit, right, with the 2 plus h part, right? Now, on this one, right, you would do your table start at 3, right? There you would want 3 to be in the middle of your table because it's x approaches 3. So this is what x is approaching, okay? So and again, this one doesn't have anything to do with derivative. It's just a limit problem. So I'll probably give you some limit problems like this. Now, I might even give you some limit problems like this one. I can't remember what this one comes out to. I think it's 1/6. We're going to do it here in a second. I think it comes out to, or 1/9. I think it comes out to 1/9. I think it comes out to 1/9. We're going to do it here in a minute. But I might even give you this problem. I might even say show that justify this limit using a table. Okay? And so you might, so you type it in, you look at your table, and you see that the values it's approaching are 1/9. Okay? Or I'd probably give it to you as a decimal maybe, or whatever. So you would just do your table, and it should show that, yes, that's where they're meeting. Because if you're using a table, what the heck? We know we're going to get it. You know, we should get it. So I might even put the answer out there. And now I'm just giving you a point for getting your table, having your table accurate, that kind of thing. Okay, well, let's do this one, though, without a calculator. So let's say this is on the no calculator part. So it was on the calculator part, easy. We do our table just like we did. Let's say this was on the no calculator part, and we were going to do this one. Okay, go. I think I lied about it being 1/9, but it's close. Okay, I'm going to put the answer up. If you don't want to look yet, don't look. Got the negative when I did it, right? Should be a negative. The red here is showing the bow tie, right? Bring the x over there, bring the 3 over there. So it's 3 minus x, and then the common denominator is just those two multiplied together, 3x. Or you could say, well, the common denominator is 3x, so I'm going to take top and bottom times x. Take the top and bottom times 3. On this one, it's doing the same thing, getting the common denominator. Okay, now remember what we do at this bottom, we've got a fraction divided by x minus 3, so it's like invert and multiply. Dividing by x minus 3 is the same as timesing by 1 over x minus 3. Right? Now, some people just say, hey, the top one here cancels with the top one down here, or the bottom one here cancels the bottom one down here. That's true. Okay, you can think of it that way as well. But again, they don't quite cancel. We got to pull out a -1, which turns that into an x minus 3, right? Like that. So we can cancel, and that's where the negative comes from. Now, the whole point of doing that is so we can plug a 3 in for x, or 3 in for x. Because up here, and I skipped over that, we should have done substitution first. So we should have plugged the 3 in for x. 1/3 minus 1/3 is 0. 3 minus 3 is 0. 0 over 0, so we keep going, and we do our algebra. Okay? Let's do this one. So we've already did, when we did the long way earlier, we did a factor and cancel one. When we did that one with the definition of the derivative. So that was one of the algebra things you have to do. One of the other ones is common denominator, and then, of course, we have the last one here, which is the conjugate method. Of course, you substitute first, to see if that works, but it doesn't. All right, and so here we go. Conjugate method. 2 root 2. We got radical x minus radical 2. We're going to multiply by radical x plus radical 2. Wherever the radicals are, that's what you're looking for, the conjugate. Okay, because when we FOIL this, radical x times radical x is x. Outers and inners will drop out. Negative root 2 times root 2 is negative 2. And of course, the top, those just cancel. You just leave that alone. Those just cancel, which allows us to plug in our 2 for x. We get root 2 plus root 2, 2 root 2. Okay, so you'll have a few of those limit problems where you do some algebra like that. Okay, if we check with our notes here on what we've talked about, let's see what we've covered here. So we have, whoops, wrong section. If we look back here, so we have done, talked about this the long way. We still need to do maybe a shortcut practice. We've done all this limit stuff now, calculator tables, that kind of stuff. Maybe the only thing we didn't talk about, which I think is probably the easiest part of it, is if you have a graph. I guess the only limit thing we didn't talk about is if you had a graph and you had this coming in like this, and then you had this coming over to here, and then you had a hole, and then you had a point, and then you had the graph went up like this, and then you had another hole, and then it came down like this. All right, let's say that's at 1, and let's say that's at 2, and let's say that's at 3. Okay, so I guess we could cover this here real quick as it relates to limits. So what is the limit as x, and let's say this is 1 right here, and let's say this is 2 right here. So what is the limit as x approaches, and these are all at the same place right here. Make it a little bigger. Okay, there you go. What's the limit as x approaches 1? Does not exist. What's the limit as x approaches 1 from the left? The car on the left is 2. What's the limit as x approaches 2? The cars meet right there at 1. The limit is 1. What is the limit as x approaches 3? 2, right? Okay, so the limit exists everywhere except at 1, where there's this break, right? The cars don't meet at 1, but the limit exists everywhere, everywhere else. Let's talk about continuous. Is this function continuous at 1? Is it continuous at 1? What's continuous mean? Don't have to lift your pencil. Is it continuous at 1? No. Why does it fail? You have to say more than because there's a break. You have to say it's not number 3, it was number 2, but I don't care if it was number 3 or number 2, what number it is, but you're going to have to write it out. You're going to have to write out this. So if we get a question about why something is not continuous, why a function is not continuous in form, I give you a graph just like that and say, where is it discontinuous? Or is it continuous at 1? If not, why not? The limit doesn't exist at that point. That's what you would say. Okay? At 2, is it continuous? You have to lift your pencil, don't you? Why is that one not continuous? This one right here. There is an output at 2, f of 2 does exist, and there is a limit. They're just not the same. The limit is 1, that's where the cars meet, but the output, f of 2, is up here. So number 3 fails. The limit does not equal the output. And is the function continuous at 3? You have to lift your pencil. The first thing in here is the function must be defined, and there is no output at that point, and so therefore the function is discontinuous at 3. So there's those 3 different ways a function can be discontinuous, make you lift your pencil and have some sort of break. The limit doesn't exist, the limit doesn't equal the output, or there is no output. Okay? So those are some questions we might ask about limits with a graph, or some questions we might ask about continuous, a continuous function. Is it continuous, and those kind of things. Okay, so that hits what we learned in our notes there. And so back to this, and so that takes care really of those kind of things. And then that leaves us with the chart stuff. Okay, and so we've got a little bit of time here. So one of the things we said with the chart kind of stuff is we talked about this capital F business, right? Capital F, little f, f prime, that kind of thing. So little f is the same as big F prime, right? Big F prime is the same as little f. So when it comes to the chart. So when is big F increasing? Well, that'd be when little f is positive. And when is big F concave up? That would be when little f is increasing, right? So still knowing the chart and those connections, right, it would be just in this order. So the top row of the chart could be big F. The next row of the chart then would be little f, or big F prime. Those two are interchangeable, okay? And so I might give you some questions like that. Might give you a little f graph and ask you some questions about big F, or give you a big F graph and ask you some questions about little f, and so forth. Little f is the slopes of big F, that kind of thing. All right, so just that's straight out of chapter 1. So knowing the chart and those connections is important. Okay, the last problem, we'll write it down here, but we may not get time to go through it here completely, but we can talk about it when we're finished here, is let's just talk about this max min. Now this would be like section 2.4. This would be like number 19, number 20, Number 21, we did in our homework. We did 54 yesterday, where we talked about that, the particle moving. When's it moving to the left, which is when its velocity, the derivative, is negative. So that would be that kind of a question, okay? So using an equation, use our power rule. So let's say we had f of x equals 2x cubed minus x squared minus 3, and we wanted to find local extrema. Now, what's local extrema mean? Min slash max, right? Now, you look at stationary points, right, but that's not the same, right? Local extrema is a min or max, not a flat spot. So local min or max, right? So this is where we do what? Let's just talk through it here first. What do we do for a problem like that? That's a number line, which starts with doing the derivative, shortcut way. Doing the derivative, we figure the important part of it. Setting it equal to 0, because that's what finds our stationary points. Number line, and then all that good stuff. Okay, so we're going to do that until we get interrupted. So you can go ahead and work on that. And then we'll come back and finish it afterwards. And then I have one other thing to talk about, and then that should be about it. Now, I might also make a comment here that if this was on the calculator part or the no calculator part, you would still have to do almost all of the same work, okay? You would. It's not like you would graph this thing and see where it had local maxes and mins. That doesn't work. You can't do that. You've got to do the derivative, set equal to 0. If you had the calculator, you could have that maybe solve it for you, for example. You could do that. But that would be it. All right? You might not have to factor and then solve. Maybe you could let the calculator solve it when you set your derivative equals 0. You're still going to have your number line. But maybe the number line can help you, or maybe the calculator can help you plug in your values, to get your number line. Get your positive, negatives on your number line, that kind of thing. Whatever the case may be. But otherwise, you would have to have all that same work. I may put it on the calculator part just to try to balance the two parts out. So they're maybe equal time or something like that. But well, she is going to be on the math office, working on her quiz with the flashlight. At this point in time, he said that was preferable to doing. She's at my desk back in the corner. So let me turn the lights off.
Yeah, I love it. Just kind of like power. Yeah. Oh, yeah. Oh, do that.
Power. Yeah, power.